Let's get started. Lesson 28, Ohm's law. We will be able to use Ohm's law in calculations. Now, ultimately, last lesson, I wanted to talk to you about resistance, and it's kind of a bit of a silly exercise because I was supposed to talk about resistance and then I didn't. But what I want you guys to do now is we're going to learn about Ohm's law and what Ohm's law is and how it can be used in calculations. Ohm's law is essentially the link that brings voltage, resistance, and current together. So that's what we're going to be looking at. That's what Ohm's law is. It's the link between all three of those things. And once you understand Ohm's law, it usually helps you understand all of these three things a bit clearer and how they're linked together. Remember, voltage has got to do with the energy in each coulomb. The resistance is, we'll talk about the resistance now. The current is the speed, or how many coulombs per second. All right, resistance. Give me a quick second. Sorry, I just got to deal with something, but 1 second. Yeah, so let you out. Sorry, guys. Resistance is a measure of the oppositions to electron flow. It is measured in ohm and it has the symbol R, so we call it R. And resistance, and the ohm symbol looks like, essentially, if you've never seen it before, it's omega. You can just draw it to look like a pimple. That's fine, because in most circumstances, that's what it is. Okay, resistance can be thought of as the energy or voltage required to move electrons at a particular current or speed. So let's just say I've got this, pipe, and in the pipe we've got a bunch of rocks. Or you can maybe think about this as a river, up to you. And in order for the current the electrons to pass through, they have to negotiate this complicated path. Now, the more rocks that are in there, the more energy I'm going to need to push around this in a fast way. If there weren't many rocks, I could just go straight through from one side to the other, from one side to the other side in a very, very, very quickly. Because there's extra rocks, in order to get from one side to the other side very, very quickly, I need to have a lot of energy because I'm doing a lot more moving around, a lot more jumping, a lot more pushing against rocks. So that's a way you can think about resistance. The term resistance usually, and that's where this formula here comes in. Now this formula, R equals V over I, this is Ohm's law. This is Ohm's law. Usually though, it's not given as R equals V over I. It's usually given V equals IR. But this is a good way to look at Ohm's law initially, because what it does, it tells you what it is related to the things we already know. We already know that in order to get as the voltage as if your current goes down, if you're moving very slowly, so let's just say your electrons are moving very slowly, there's not many electrons moving past every second. The flow is very, very, very small, or low flow. And you might say, okay, yes, so what? But if you've got a low flow, but you're pushing really hard, you have a high voltage, that means there is something going wrong here. You're pushing those electrons as hard as you can, but they're just not flowing, then you must have some resistance. And that resistance is this. How quickly are they moving? How much energy are you putting in divided by how quickly they're moving? Because if you're putting a lot of energy in, and those electrons are flying out like, bullets out of a gun, then you know that you've got very little resistance. But if you're shoving those things as hard as you can and they're not moving, then yeah, there's probably some kind of resistance. Now, resistance obviously takes up energy. As the electrons are pushing their way through that wire, and if it's really hard to push their way down that wire, they're going to have to spend some of their energy to get through there, spend some of their voltage to get through the wire. And of course, we refer to that loss of energy by resistance as, well, how does it usually emits it as heat. What type of heat are we talking about? Well, we're talking about, it's going to increase its temperature, and it's going to, as its temperature gets increased, then it will emit that energy as heat, because the energy will be released from it. To go back into a little bit about thermodynamics, why is it releasing it as heat? Because the molecules, because the particles, the electrons are pushing against other things, it's getting internal friction. So it's like essentially every time the electrons bump past one of these rocks, it's going to make a little bit of friction, and friction is going to convert that energy into an increase in temperature. It's going to start the electrons, it's going to start the molecules inside the wire moving, and that's going to vibrating, and that's going to, of course, mean that they're going to emit temperature and so on and so forth. I won't go into too much detail there. We've already spent a whole term talking about thermodynamics, so let's leave it at that. Okay, so the next idea is, oh, by the way, the obligatory pun. I love this pun. It's a great pickup line. Hey baby, would there be any resistance if I took you home? I'll let you know, it doesn't work. I tried it once in an Irish bar. I was very drunk. Yeah, it doesn't work. Anyway, what does resistance look like? So hold on, just got my dog inside. He's outside whining. Give me a second. Sorry, dog's being a bit of a sook. He thinks, oh, dad's home. I can just, get all the attention. Not realizing I have 23 students listening to me. So at the moment, this is the same picture we brought up 3 times. So let's look at this picture one more time. We've got a big tank. Big tank is full of water. This is our voltage, or actually, you know what? This is our EMF, our electromotive force. This is the thing that's pushing the water out of the tank. Okay, it's applying the force. The flow of water here, this is our current. This is the how quickly that water is flowing. So where's the resistance? Well, let's take, what would happen to the current? What would happen to I if I was to add a rock? So if I drop a rock into this pipe, right? What that's going to do is it's going to make it harder for the water to get through the pipe. Okay? Initially, the water could just push through because that's what the voltage did. But now it's harder for it to push through. So because it's harder for it to push through, less water is going to come out. So therefore, the current is going to decrease. The amount of water flowing through is lower because there is something opposing the force of the water. The exact same thing occurs in a circuit. If I have a circuit here, the electrons are coming out of the negative side. They're going through the circuit. They're happy, and then they're going to go through here. And in fact, because we've got a lot of electrons, I'm going to do a big, thick line here. Great. But if I was to put a resistor into that circuit, I put this big resistor in here, suddenly that's going to affect things. Because now the resistor, just like the rock, means that only a little bit of current can get through at a second because it's impeding the flow. So that means only a little bit of current can go through the whole circuit. You can't have like a little bit of current here and a lot of current here at the bottom, because then you would end up with a big bottleneck, and that's wouldn't work, because if you had a big bottleneck, that means you've got lots of electrons in one place. Electrons don't like that. But of course, if you reduce the current, right, that means less, the light bulb will become dim, because of course it's not able to get as much. It needs a lot of voltage to push its way through that resistor. So now the light bulb doesn't have as much voltage. It doesn't. The electrons can't spend all their voltage at the light bulb now. They have to keep some voltage in reserve so they can get through that resistor. And that's sort of how resistance works in a circuit. Now, what are resistors? Just because I talked about resistor here, what is a resistor? I'm gonna like sort of break away here for a second. I don't know how much of this stuff that you need to know for the according to the government. So I'm just going to talk about this because the textbook talks about it, the other textbook talks about it. So I think it might be a little bit important. So I'm just going to touch on a couple of these things. You don't have to memorize them or write these things down. I'm just going to talk about them. So resistors are often used in electronic circuits to control the amount of voltage available in the circuit. So for those of you that have done engineering maths, you'll also have an advantage, but for everyone else, just a quick side point. If I've got a battery and I've got a resistor and I've got a light bulb, then what that's going to mean is that this is a 12 volt. If this is a 12 volt battery, then what would normally get dropped over the light bulb is 12 volts. But now if I put a resistor in, well, what might happen is I might lose maybe say 6 volts to push through that resistor. So that means I only have 6 volts left to drop over the light bulb. Sorry, it's in red. It's actually really hard to read that. Sorry about that. But yeah, the idea is that as you increase the as you add a resistor, it just means, hey, this is going to get less voltage, which means if it's less voltage, it's less bright. There are 3 types of resistors. The first type is a composition resistor. Composition resistors have usually got carbon in them, and they sort of like impede the flow by carbon. The next one is a wire round resistors. These guys are old, but you can still find them. Like, for example, we have some in the physics lab because the physics lab is so old. But these are the easiest ones to understand. The only reason why they're resistance is because there is so much wire that the electrons have to go through. Usually these wires are made out of a metal that is heat resistant, because obviously if they're going to build up heat because they're resistors, and so you want to make sure they can dissipate that heat. The last one is called a metal film. So that's usually when they've got like pieces of metal that conduct electricity but don't conduct it very well, or they've got, I don't actually know how they work very much. I really should have, note to self, I really should have investigated these before I started trying to teach you guys. But these are the 3 types. By all means, look them up, become more of an expert than me. You know, figure out what is, when we say composition, what is the composition? I know it's a carbon composition, but it doesn't say, I don't know how the carbon works. So by all means, look them up. And yeah. Now, they often have color-coded bands on them. So examples of those color-coded bands are here, and you can see on them here. These color-coded bands allow users to know how much resistance they offer. Now, normally I would skip over this part, but then I noticed that it showed up in 2 of the different textbooks. So I'm going to quickly talk to you guys about this. I'm going to explain some of this. Okay, I'll start off with the resistors first. The values of resistance we've just said are specified in ohms, or kilo ohms, K-ohm, or mega ohms, M-ohms. So it's a kilo ohms are going to be 1,000 ohms. and a mega ohm is going to be 1,000,000 ohms. This is actually important because there will be questions where it's like, oh, a 10 kilo ohm resistor, and you've got to remember, oh, 10 kilo ohms. I can't just use V equals IR straight away. I've got to make sure that I remember that's 10,000 ohms, not whatever. Resistors are not polarized, so it doesn't matter which way you put them into a circuit because they will, resist. It doesn't matter if the current is going from left to right or right to left. This might seem like a really weird sentence, but the reason I'm putting that in there is that later on we're going to talk about devices that are polarized. If you don't put them in the right way, then the whole circuit won't work. But I'm just going to say resistors don't care. Now, some resistors can have their resistance changed, by dial. We would call these a variable resistor. So a variable resistor can change its resistance, and you can go from like 1 ohm to 10 ohms. And that's really where might this be really important. I love that here is an example. That would be really good in something like volume control. You want to be able, if you've got a resistor, then you can change the resistance by, changing the dial, and then that might mean that your speaker. Can I draw a speaker? Oh crap! Yeah, that's a bad speaker. Sorry. Oh, actually, you know what? There you go. It's got a music note on it, so it has to be a speaker. So yeah, obviously, as you turn the dial, it might make it emit more sound energy. You can also use it as a dimmer switch for lights, whatever. It's just a really good way to change that humans can interact with the circuit. There are two symbols, the European symbol and the Japanese symbol, or the USA symbol. I'm really bad with circuits, and I will usually switch from one to the other because I'm bad. I really should just stick to the European one though, because I think that that's the one that they put into the Year 12 exam. So that's probably what I'm going to stick to if I remember, but I do have a tendency to switch and sometimes use them. I like the USA and Japanese one because it actually that's what a resistor does. It's a long wire that slows down the path of the speed of the electrons. Now, this picture over here on the right is called the resistor color coding chart. Now, I personally don't think it's valuable for students to memorize this chart or even to fully understand this chart. But it seems to have shown up in a couple of different textbooks, and including your textbook. So I'm going to briefly explain how it works. Now, how it works is you have these colored bands. Now, those colored bands tell you the resistance of the circuit, of the resistor. So, for example, the first band represents the first digit. If in this case it's green, then that means we would go, okay, where is green? Green is here, 5. So that means this has got a 5 at the front. Then the blue line represents the next digit. So if I go blue, 5, 6, okay, so 56. The third digit, well, in this case, the third digit is our last digit. So because this third digit is our last digit, that means it's going to be the multiplier. Now you might say, well, how do you know it's the third digit and not the, how do you know it's the multiplier, not the third digit? Because I know it's the last in that list of 3. So this is a multiplier of orange, so that means it's going to be 1,000. So I'm going to do that. So that means that this resistor is 56,000 ohms or 56 kilo ohms, which is what it says here. Now, what does this gold band represent? Well, gold band represents the tolerance. Gold is plus or minus 5%. Hey, look at that. It's an error margin. It's an absolute error because we don't know exactly what the error of the resistance is. So this is an error. Remember, that's why one of the reasons why I spent so much time talking about errors, 5 or 6%. So plus or minus 5%. For the one on the bottom, we've got a yellow, which means we've got 4. So that means we've got a 3-digit number and then a multiplier. So the digits are 4 for yellow, 7 for purple, 0 for black. Then there's a red multiplier. So red would be 100. And then we've got, so that's going to be 47000 or 47,000 kilo ohms, 47,000 ohms, or 47 kilo ohms. Did I get it right? I got it right. And then we've got this brown, which is 1%, so plus or minus 1%. And that's the tolerance. So we know that it pretty much is very likely to be 47 kilo ohms. It's 47 kilo ohms. 1% of 47 is going to be 0.4. So it's 47 plus or minus 0.4. Now, there's 2 reasons why I don't like teaching this. One, because ultimately you're going to have to look these things up. And a lot of you guys are probably not going to do physics, so knowing how to read a lot of you probably aren't going to do engineering to the point of electrical engineering, and so to the point where you need to know the resistance. So it's unlikely that this will ever be useful to you. So I don't like teaching that for that reason. The second reason why I really hate these things is because of big Mr. Griff. Now, this is why I hate these things, right? So you learn how to read these bands, and you're like, okay, great, awesome. So what? So then you get a resistor. Here is a resistor. Now, can you guys see the bands? No, because they're so goddamn small. I hate them so much. Because, like, if I bring this, and I'm not going to be able to get this in focus, if I bring this really close to the camera, even when it's like this close, it is really hard to see the bands. And I've got glasses, so I struggle. If I bring this out slowly, we can see that this has got 2 bands. It's actually got, so this one here happens to have red on the end. So it looks like it looks like that it is a red, and yeah, you can't even see the colors very well. If you're colorblind, you're stuffed. This is a red, brown, yellow, orange. And so you go, okay, red, brown, orange, I guess you could figure that out. So you would go, well, what's going to be red, brown, orange? And you go back to your, point. Whoa, okay. Red, brown, orange, go back here. Red being 2, brown being 1, and then orange being the multiplier, going to be 1,000. So it's going to be red, brown, so 21,000 ohms. And then you look on the packet, and the packet for this particular one says it's 330 ohms, plus or minus 5%. So that means that brown at the end was actually gold. And so therefore, yeah, sorry, I'm going to quit complaining. I just hate it. Sorry for the complete side point. This lesson's a bit weird. I'm sorry, but yeah. There is another thing about resistors though, that I do want to quickly say. Resistors can also have different ratings depending on their ability to resist. Like, what do you mean? Well, they have different sizes. You can have really, really tiny resistors, or you could have big, chunky resistors. And the size of those resistors actually gives you an idea of how much. So what we commonly resistors are 1/8 of a watt, 1/4 of a watt, 1/2 a watt, 1 watt, or 2 watt resistors. You're like, okay, so that means if you have let's just say you've got a 1/2 a watt resistor and you have a voltage, if you try to put 12 volts in and you try to put that in at we'll go with something like 0.12 we'll go with 0.1 amp or 100 milliamps. If you try and do that into this resistor, you'll kill the resistor, because the resistor, if I go power equals V times I, that's going to be 1.2 watts. You're trying to put 1.2 watts through a 1/2 watt resistor, you're going to kill that poor resistor. You need to get a bigger resistor in order to make this work. Otherwise, it'll be destroyed. So high power resistors can be used in high power devices. If you're just looking at something like, a little toy car, then maybe you can probably get away with 1 watt, 1/2 a watt resistors. But if you've got like a really big, like a lawnmower or something, then you're going to need big resistors in it. So that's all the stuff about resistors. The last little bit about resistance is just in general, we've already talked about this, but just another reminder, high resistance to electron flow is going to be something like an insulator, like wood or air or plastic. Things that have low resistance to electron flow are conductors like copper and gold and water. We've already discussed this back when we talked about current flow and what can current flow through. So pretty much wrapping up, this brings us to V equals IR as a formula. Ultimately, I've said this multiple times, that the current is the flow of the actual electrons, or like the flow of a river. When you think about electric circuits, the current is the actual substance that is flowing through the wires, the electrons. We're talking about how many of these water droplets are going down the river, how many of these little electrons are moving through the wire, how many of these charges are moving through the wire at a particular time. That's what we talk about when we talk about current. Voltage is the push, the force that pushes the electrons. In this picture, it's gravity, because the gravity is forcing the water to fall downwards, and it's going to force the river to keep moving. Gravity in this case is the pushing force that pushes the water down a slope, and voltage in a circuit is the push that forces the electrons to want to get to the positive side of the battery. But the resistance is how difficult it is. When you have a lot of rocks in this river, it's going to impede the flow. So even if you've got that big push from the fact that from gravity, if you've got a lot of rocks in your river, it's going to slow down the current. It's going to mean that less water can pass through. So that's how all these things are aligned, which brings us to the formula. Ohm's law, V equals IR. Now this is the big boy here. This is the one that we rely on the most when dealing with electronic circuits. Don't get me wrong, the other formulas are useful, but this is the one that matters probably the most. Voltage is equal to the current times the resistance. Now, why I always come back to this one is because there are so many different things that we can talk about when we talk about this formula. So And I usually like to do them by by doing different things. I'm going to talk about this formula now and how these things relate. So I'm going to start off with voltage. I want to keep the voltage constant. Let's keep the voltage constant. If the voltage is constant, right? And what that means is that you're using a battery, like you're using a 12-volt battery, and that's it. You're not going to mix it up and grab a 10-volt battery or a 4-volt battery. You're using the same voltage battery. If you've got a voltage, and let's just say if the current goes up, so if you want to increase the speed of the electrons through your circuit, if you want to make more flow happen, the only way to make more flow happen, right, without changing the voltage is to decrease the resistance. The only way to make the current move faster is to lower the amount of resistance, to make the resistance lower. So it's easier for the electrons to move through. You could say as well, if you have a fixed voltage, as the resistance goes up, as it gets harder for those electrons to move through, the current will go down. The speed of the electrons will move will be the same. If you increase the resistance, the current will go down. You can explore this using actual numbers. If the voltage is 10, and then you've got the current is 2 times 5. If you increase the resistance, let's say we increase it to 10, then you double the resistance, and that means the current is going to go down. It has to go down to 1 to make sure this still equals 10. So if you increase the resistance, you must decrease the current. So that's voltage. Let's make the current constant. If the current is constant, or in this case, I equals V divided by R, if the current's constant, that means as the voltage goes up, so as you add more energy, in order to make sure that your current doesn't change, you need to make it harder. You need to increase the resistance. Think about it, I guess, if you want some students to run a marathon, and you're talking about grade sixes, a race, talking about grade sixes, you might want to give them a short race. If you're talking about year 10s though, who have more energy, more voltage, then they'll need a harder racetrack. So you need to make it harder for them, maybe make them go uphill. That's the only way to make sure that they will get the race done in the same speed. The opposite's true, of course, if you decrease the voltage, if you give the circuit less energy, in order for the current to move at the same speed, you need to decrease the amount of resistance. The last thing here is going to be resistance. So the resistance constant. In order to make the resistance constant, you need to have the resistance is going to be the voltage divided by the current. I've already talked about this. In order to make this work, as the voltage goes up, as you give those electrons more energy, in order to make sure that the resistance, as the voltage going through a particular circuit, let's maybe say it's a light bulb. If you want the voltage drop over the light bulb to be the same, then you have to also increase the current. As the voltage goes up, the current's going to go up too. They're linked. And so on. And as the voltage goes down, the current's going to go down. So everything is linked. And that's why I love Ohm's law so much, is because it shows how these ideas are linked together. Have I gone way over the time limit? Oh, crap. What time is it? No, I'm good. I'm good. I'm all right. Sorry, I just panicked there. Sorry, ladies and gents. I have talked for a while, so thank you for paying attention for so long. I'm going to talk to you guys. Let's do. So I've got half an hour left, but I want to give you guys some time to work on some problems. But I'm going to finish this off. A torch uses 9 volts battery power and has 100 milliamps of current through it. Through the circuit, what is the resistance in a lamp? How do you solve a question like this? First, let's pull out the information. We've got a 9-volt battery, so an EMF of 9 volts. Cool. Voltage equals 9. Done. With 100 milliamps of current. I equals 100 milliamps. But we don't use 100 milliamps in our answer. We're going to use 0.1. We're going to convert this to, we're going to convert it to amps. We want to know what R is. So we take the formula, V equals IR. We're going to rearrange it. V divided by I is going to give us R. So therefore, R is going to be 9 volts divided by 0.1 amps, which is going to give us 9 divided by 0.1 is going to give us 90 ohms. Perfect. Questions? This is very similar to the types of questions that you guys have seen before, on the type of equations you guys have seen before. Okay, cool. Thanks, Kelvin. Yep. So you guys have done these sort of things before. All right. So it's just pulling out the important facts. In this case, it's only there are only 3 things in the equation, V, I, and R. And once you've got those important facts, you can do this. Now, a mean question might then sort of say, hey, you know the current, so you can work out how many coulombs are coming through every second. You know the voltage, so you can work out the amount of energy each coulomb has. But I'm not gonna torture you guys too much with that sort of stuff. Ultimately, once you understand how voltage is related to coulombs, how current's related to coulombs, once you got past that, we're just going to talk about voltage, the amount of energy, current, the amount of the speed of what's going on. Let's grab a look at this one. You know what? I want you guys to work this out. I'm going to give you guys a little bit of time to figure out what the answer to this is. So I want you guys to work out this one on your own. All right? Okay. 2 people got the answer already. 16 ohms. Let's grab a look at this one. I didn't realize that this was the same type of question. I really should have done a current question, but that's okay. What is resistance for a motor? V equals 12. I equals 0.75. Skipping a step here, but hopefully you're good. R is unknown. V equals IR. And therefore V divided by I is going to give you R. 12 divided by 0.75. 12 divided by 0.75 is going to give us 16 ohms. Perfect. All right, so just a quick example for you guys. Cool. I did not spend very much time working this out because, yeah, you guys are beginning to get familiar with this. And I'm going to get you guys to get a fair bit of practice in for Ohm's law because ultimately it's a pretty important skill to be able to do. The last little bit with Ohm's law and resistance is to talk about Ohm's law and ohmic resistors. Now, most resistors, like most of them, in devices in a circuit obey Ohm's law. They follow Ohm's law into calculating things. As the resistance increases, the voltage must increase to keep the same current. Again, that's the same idea I talked to you guys before. Now over on the left here, and then you might want to, if you are taking notes and you are doing this, you don't have to do this necessarily. You don't have to do a whole big graph or anything. You can just draw a quick line. But on the left here, I've got two things. I've got I and I've got V. Now, as the voltage increases from 2 to 4 to 6 to 8 to 10 to 12, the current will increase from 1 milliamp to 3 to 4 to 5 to 6, because as we push the electrons with more and more and more energy, we're going to be able to see those electrons move faster and faster and faster. And if we were to plot this, we would see that for 2 volts, we have 1 milliamp. For 4 volts, we have 2 milliamps. These really should be the other way around, but there's another 6, 8, 10. And we can see now that if I was able to draw a straight line, that we would have this line represents the curve of voltage against current. And it's a straight line. Now we know it's a straight line, which means it's linear. And the other thing we know about that, the reason it's linear is because I relates to V in a linear fashion. Okay, but you might be like, I want you guys to stop for a second, just because I've actually taught this before to in engineering maths. And again, if you haven't done it, don't stress. So if you're seeing this for the first time, just accept the linear line. But what I want to talk about now is I want to talk about the gradient here. The gradient of this line, right, is rise or run, which is the current divided by the voltage. And I'm like, okay, if I take V equals IR, and if I take the voltage divided by the current, I get R. But that's not what I've got here. I've got I divided by V. So that means the current divided by the voltage is equal to 1 over R in this particular circuit. And this is actually what this is how Ohm originally came up with Ohm's law. He would look at the circuits like this. And the reason you might say, well, why didn't he just change the current? Because you can't just easily change the current. You could easily change the voltage by getting more and more bigger and bigger and bigger voltmeters, bigger and bigger power supplies. You can't just change the current easily. So if I was to look at this part of the graph here, the rise is from 2 to 4. So that's a rise of 2 milliamps, and it's a run of 4 volts. So if I go, I'm going to change colors now. If I go rise of a run, and I go a rise of 2 milliamps, so 2 milliamps is going to be 0.002 milliamps divided by 4 volts. That's going to give us 0.005. I'm going to just get my calculator because I'm going to get this wrong. And I know that if I get this wrong, someone's going to be, 0.005. Now that is not the resistance though. Remember, resistance equals 1 over the gradient. So that means if I go 1 divided by 0.0005, that gives me 2,000 ohms, which is exactly what I've got written here, 2,000 ohms. Now, you could also just do this for any individual point. You could take this point here and say, well, it's 4 volts divided by, its current is 2, so divided by 0.002, and that will also equal 2,000 ohms. I just want you guys to be able to see how this compares to the gradient, and then how this also can be just done by reading off values. What's really important with the gradient part here is to remember that R in this circuit is the gradient is, R equals 1 over the gradient. That's how we work out the resistance. And the reason it's 1 over the gradient is because of this idea here. Now, this is a bit weird, but I'm hoping that you guys get it. If you don't stress too much about it. We're going to do another example in a second. I haven't got too much time left in this lesson, so I just want to make sure that I get through it. So yeah. So next step is to talk about non-ohmic devices. So it's not all rainbows now that we've done all this hard work to learn about ohmic resistors, only for me to tell you, guess what? Not everything is ohmic. So in an ohmic resistor, the voltage drop and the current drop, the current stays linear, but in some resistors, they don't stay linear. An example is a light bulb. You might not be aware of it, but a light bulb is actually technically a non-ohmic device. We usually say, usually a light bulb we say is an ohmic device, but what we would do is we'd look at this part and say, yeah, it looks pretty much like a straight line. But as you go further and further up, you will see that as you apply more and more and more voltage, the current doesn't go through in a linear way. You would expect that if you went from 10 volts to 12 volts, you are giving your electrons more energy, so they should be able to push through that light bulb faster. But when you get to between 10 and 12 volts, it doesn't matter how much you're pushing those electrons, they're just not going to be able to move very fast. And that might be caused by the heat. It might be caused by the heat of the light bulb. It might be caused by the size of the filament, the wire filament. If you've got like a small pipe, doesn't matter how hard you push, there's only so much water that can go down it. So these are non-linear. So we refer to them as non-ohmic. Diodes are the same. Diodes are weird, and we're going to talk about these in a bit more detail later on. But a diode it will only drop the same amount of voltage. It will always drop 1 volt, and it doesn't matter, its voltage is always 1 volt. And as you try to add more and more voltage, it doesn't actually increase the voltage drop, it just increases the amount of current that can go through there. So it's almost like the opposite of this one on the left. The left, you increase the voltage, the current doesn't go up much. On the right, you increase the voltage of the circuit, the diode doesn't drop more voltage, but the current goes up. There are other factors that can affect the resistance or of a circuit, including the light, how much light's on it, what temperature it is. Maybe sometimes it can be affected by magnetism, but non-ohmic devices are a bit odd. We're going to go through these examples in a lot more detail later on. But the last idea, really quickly, non-ohmic devices just means that they're not linear. So an example of a non-ohmic device will not follow a linear graph. So that means that if I start from my voltage in volts, if I instead, notice how this one's the right way around, BI, whatever. We go with 2, 4, 6, 8, 10, 12 volts. And then on the left, we're going to do this in, we're going to do this in amps. We're going to do this in 200 milliamp blocks, I think. So we're going to go with 200, 400, 600, 800, 1,000. This is milliamps. So that's 1,000 and 1,200. So the idea of how a non-ohmic device works is, okay, for 2 volts, we're only going to use 1 milliamps. It's not even going to show up on our graph. For 4 volts, well, we're only using 10. It's still not going to show up. For 6 volts, though, we're using 100. Okay, that's halfway. For 8 volts, we use 1,000. So that's up here. And then for 10 volts, it's okay. It's, yeah. And we can see it very quickly shoots up and just, keeps going up. And the non-ohmic device just doesn't follow Ohm's law. It just doesn't work the same way. As you increase the voltage, instead of it being a nice straight linear line, it turns into it can be an exponential, it could take the form of a logarithm, it could take the form of some weird like linear thing. Whatever the point is, it's non-linear. If that's all that you've got, then that's all that I want you to get. It doesn't form a linear line. So if it doesn't form a linear line, how do you deal with stuff? A 60-watt incandescent light bulb has an IV characteristic as shown here. Calculate the resistance of the light bulb at 175 volts. First things first, this is a non-ohmic resistor. And I've already talked about this 3 times already, but can someone tell me, how does Mr. Greer know this is a non-ohmic resistor? What is the clue? Please make chat I've got this right. It's not linear. Yay! It's not linear. That is correct, because it's non-ohmic, because it's not linear. This should be linear. As the voltage goes up, the current should go up. As you push more energy, as you push those electrons, they should move faster. What you're saying in this one, as you push those electrons, the electrons don't necessarily move faster and faster. I guess that you could say for a light globe, and this is, I don't know if this is a real term, but I guess you could say it's almost semi-ohmic, because as the voltage goes up, the current does go up, but it just doesn't go up in a straight line. So how do you measure this? Calculate the resistance at 175 volts. Where is 175? 100, here's 150, here's 175. It's halfway between 150 and 200. If I go up here, I hit the graph at this point here, what type of current am I seeing at that point? Well, at that point, I'm halfway between 200 and, let me just double check. That's not 300, that's 250. I'm halfway between 200 and 250. So that's going to be 225. So the resistance is the voltage divided by the current. The voltage is 175 volts. The current is 0.225. Because remember, 225 milliamps is actually going to be 0.225 amps. Which is going to be, and I'm going to quickly check chat because I want to make sure that I haven't made a horrible mistake. Answer 225. Kelvin's given the answer already. Let's see if he's right. 175 volts divided by 0.225 gives us 777.77. Let's just go with 770. You know what? Stop it. 778 ohms. You can just and you know what, Kelvin, there's nothing wrong with your answer. You've just gone to 2 decimal places. I just felt lazy, so I'm just going to go to 0 decimal places. There's been a couple of questions that people have asked about, you know, how do I deal with significant figures? I guess this is an idea. You would quickly say you don't need to worry about them too much. I actually don't care if you make a mistake with significant figures at the moment. It's going to be later on that I might, during exam time, that we start to get a bit more strict. The idea would be, this is 3 significant figures, so therefore our answer needs to be 3 significant figures. But whatever, I'm not too stressed. And by the way, this 60 watt isn't actually using any calculation, so it doesn't count to our significant figures. So that's it. That was a lot of stuff, and I apologize for the lesson being, holy crap, pretty much a full hour and a half. But let's just go over what we did. We talked about 3 big ideas. We talked about resistance being the rock that slows down the flow. It doesn't matter how much pushing your water does, it can't get through there. So therefore, resistance, as you increase the resistance, you drop down the current. We then talked a bit about resistors and how they work and what they look like and that sort of thing. The next big idea we talked about was Ohm's law. We discussed that as you increase the current, in order to keep the same voltage, you have to decrease the resistance. You have to make it easier to flow if you want it to flow faster with the same amount of energy. And we talked about how all these things are linked. I always think about these things, and the example that I always give, which is a bad one, but it still works, is imagine a corridor filled with people. And you want to get from one side of the corridor to the other side of the corridor. What affects you? So as your resistance goes up, you are going to move a lot slower through that corridor. I usually say the corridor, the S block corridor just before recess. You know, the kids are just not going to move very quickly because they're all going to the locker. So therefore, your current's going to go low. If you want to get through that corridor faster, though, if you want to increase your current, you should put more energy into the way that you walk, into your running. You should definitely start, you know, moving, pushing people out of the side with more voltage, more energy. If you decrease the amount of people, if you lower the resistance, suddenly you don't need as much energy to walk through that corridor at that fast speed because there's no one in your way. So all of these things are linked. Voltage is linked to current, is linked to resistance. Then the last big idea that we talked about was non-ohmic devices. We said that, and how these look as a shape. Non-ohmic devices, ohmic and non-ohmic devices are linear. As the voltage increases, the current increases. But that's not the same for ohmic devices. As the voltage increases, the current doesn't always increase in a linear way. So therefore, in order to find the resistance, you need to look at a particular point. You need to go 4 volts, how many amps, and so on and so forth. Hopefully, this lesson made sense to you guys.